所以到目前我们有什么问题呢？Okay, so now we talk about energy equation. So the energy equation basically is related to the momentum equation, especially for the mechanical energy. Okay, shall I use Mandarin? Now, I think if your English can follow, I just use the English. Okay, so you can see in the momentum equation we have a pressure and the viscosity. These two forces with contribution to the mechanical energy in the energy equation. So energy equation we can regard as thermal energy and mechanical energy. This is last week we talked about. The thermal energy is related to the heat transfer. That will relate to a temperature difference. You have a temperature difference and you have a heat. That will be the heat, or sometimes referred as the thermal energy. In the force, if we have a force, no matter pressure or viscosity, this kind of energy will become to the mechanical energy. And later on, we will compare the magnitude, the size of these two energies. You can see if you have maybe 5 or 10 degree difference, the thermal energy will significantly large than the mechanical energy. So in this case, if the mechanical energy can be neglected, because if they are small enough. So in most of the cases, if you have a significant temperature difference, usually mechanical energy will be neglected. And in the energy equation, usually they will only consider the thermal energy. This is usually you talk in the thermodynamics. And in thermodynamics, in most of the cases, you only consider the thermal energy. But in thermodynamics, they also mention in special case, if there is no temperature difference, that means they don't consider the thermal energy. Then your energy equation will become to a Bernoulli equation. That will be the consistent with the previous idea. Okay? So today we continue to talk about energy equation, and for this energy equation, in Laminar flow, we focus on the work. So the work that we relate to the external force. So in the momentum equation, we have external force like the pressure, gravity, and also the viscosity. We like to see this kind of force have some kind of contribution in the energy equation. For the purely the heat, I think this is already taught in the first law in the thermodynamics. In the thermodynamics, mostly we focus on the heat. So energy equation, from here you can see we can divide into the thermal energy and the mechanical energy. For the most of the case, we will consider the thermal energy. And why in this kind of situation, later on you will see why this will be in the most of the case, this will be considered only because the magnitude for this one usually is significant large than this one. Maybe scale is like 1 to 1,000, 1 to 100 about. So you will neglect the work part. Okay. And anyone have an idea what the difference between these two? I think last week we didn't talk about that.
The last one is definite difference. The right side is indefinite difference.
Can you swallow the food first, then talk? So that's why usually in the lecture we don't suggest students eat the food. Because sometimes they will have some kind of emergency, like a shock or something. No, I'm just kidding. So what do you think?
With the right hand side, the delta, it means indefinite difference. It's
In
not
two, what do you mean? On the left hand side,
no, the
right hand side.
yeah.
Uh-huh.
It's indefinite. It's not the same as the small d, as like the
This one.
yeah.
So what difference? Yeah, we use two different symbols, but some people can tell what the difference. And I will write down this because I think the textbook. Let me see. Textbook should use the wrong one.
Oh, it is.
Yeah, I think the textbook uses this one. So that's why the last week I talked about this, the symbol. So last week we didn't mention what difference between these two.
But I don't know English.
Yeah, you can talk in Mandarin and I can translate.
点函数跟路径函数。
Yeah, one is depend on the state function. Usually it's mentioned about state function. So this is mentioned like the initial state and the final state. I think I gave one example last week. It's in your undergraduate. in your undergraduate, when you come in, what kind of a status, and when you go out, what kind of a status. But right now you are because I teach this thermodynamics in undergraduate, but right now you are a graduate student. That step, that means that time, you are in which step? So you are in the high energy step or low energy step. That's you will use this. They already look the step. That means they already look temperature and the pressure. So they will determine their temperature, pressure, determine their energy situation. So basically, heat and the work cannot be the step, because the heat and the work is a boundary effect. This kind of a boundary effect will depend on the path. The path is how you apply the heat into this system, or you apply the work or apply the force into this system. Basically, you can make the heat. You can create a lot of heat, but not into a system. Okay, and you can use a lot of force, but if force is not consistent with displacement direction, you cannot apply the effective work into a system as well. So last week I give the example is I hope when you go out of this university, you are in some kind like the high energy state compared when you come in. That will depend on which path you are use, how you use different paths to increase your energy. For example, you have this time, you can go to a library, but you can also just create a video game. You have the same time, but you can do different things. Then you should think about what kind of activity in same university they will increase your energy, or you just waste of time. Okay. So basically, this is the pace function. I think last week we write down this, the pace function, and usually they use this, the delta, to represent. They are different from the state function. Okay, so that's in most of the thermodynamics or in some engineering mathematics, they talk about this. Then the energy, the total energy last week we mentioned about they have this kind of total energy, and basically this internal energy is related to the temperature. Okay, so this internal energy usually in the closed system is only include closed system only have internal energy. That's U in your thermodynamics. Then if in an open system, this U with summation with this work. Later on you will see that we have a pressure. So internal energy plus the pressure, that will become to the enthalpy. Okay? So in an open system, in your thermodynamics, you usually consider enthalpy, not consider the internal energy only. But basically, this corresponds to the internal energy in your thermodynamics. Okay, So if we write down the internal energy, you can write down like this. Basically, later on you can see the result. This term and this term will correspond to the mechanical energy. So later on they will be cancelled out in the work. You will see the contribution for the work and the heat. So the contribution for the energy equation, heat and the work. The heat is by the Fourier law. So Fourier law, I think this is in the heat transfer or in the thermodynamics that we talk about this. For the work, we will talk about some more detail. Last week, we talked about the work is related to the external force. And especially we talk about the service force in this system, because in this system, service force in two different phases, then we have work in and work out. So the difference will become to the system absorb this kind of work. And they have a x, y, z direction. So if we write down like this, different kind of work. This is for the work rate. So usually it's like the power. Okay. So for this power in the x direction, they will correspond to the x direction velocity. And for this surface force, what kind of component for this surface force? Last week we have equal, right? Because different kind of component, they will have a different kind of contribution. This is why I will X right now. The component for the service force. Do you have an idea? Okay, so in x direction, remember we write down this stress should be in this figure. So the stress, if in x direction, then we have pi 1 1. So what's pi 1 1? That's pressure, right? Then we have a pi 1 2. That's shear stress, and in the y direction. And the pi 1 3 also shear stress. So basic component include pressure and shear stress. So you will see the pressure with contribution similar to the Bernoulli equation. because the pressure, they will have some kind of acceleration, deceleration. So this pressure similar to the Euler equation or similar to the Bernoulli equation. But shear stress, usually we will talk about this is a viscosity force. Also, we will talk about shear stress is like a friction. So friction basically is a reduced useful energy. So your mechanical energy will be reduced by shear stress. Okay, so later on you will see the pressure still contribution to the mechanical energy, and then they can convert because the pressure can convert to the gravity. They can move up. So your gravity and the pressure can transfer. Kinematical energy can be transferred by the pressure as well. So now we become to the Bernoulli equation. But viscosity, they will have some kind of friction. So viscosity, basically, they will create a heat. They will become to a thermal energy. So your useful energy will become some part into the thermal energy. But that thermal energy will not convert to the mechanical energy. So your mechanical energy eventually will dissipate, will lose your mechanical energy. So this work, if we consider the viscosity, that means we consider the friction. Then, so last time we mentioned about the common typo for this. You can see for this case, the force direction is in the second index. In some textbook, the force direction or maybe we become to a first index. I think last week we mentioned about that. Some index in the textbook maybe it's not consistent in momentum equation. Okay, but here is consistent. Here is consistent. You can see velocity and the force direction, they are consistent. Okay, and for the service force, for this equation, that means we need to differentiate this equation become to this and this, because both velocity and this service force, they are function of x, y, z. So we have a diverge. This is differential by the x, y, z for the space diameter. So in this case, this part we rewrite as these two terms. Okay, and these two terms, if we use the momentum equation, the service force in the momentum equation is acceleration. This on the left-hand side is due to the body force, gravitational force, and the service force. But right now we rewrite this service force to here. Then we can rewrite this term to become like this term. You can see this term is same as this term. Okay. So that means if we substitute this dt dE into this equation, dq dt dq into this equation, and dw dt by this term. Okay, and this term we can write down like this term, but here this term is same as these two terms. So this energy equation can rewrite as this, because the E only left this term, okay? And for the Fourier law, they only keep this term, like the 235. Then for the dw, dt dw, the left-hand side, this term is cancelled out. We only have a second term, because the first term, like this, is the same as this term. So energy equation okay, so energy equation can rewrite as this. It's quite similar to your thermodynamics. If you look at this, become to the U, okay? Look as the internal energy. E is like the internal energy in your thermodynamics. Then for these two terms, this is correspond to the heat, Fourier law. This correspond to the work. Okay. Later on, we will see the work contribution. Just like we mentioned, this work, your stress or your service force, they have pressure and shear stress. Pressure will contribute some mechanical energy. It's useful energy that it can convert with kinematical energy or potential energy. But shear stress, that's friction. Friction we become to the dissipate. Then we become to some kind of thermal energy. They convert to the thermal energy, but we become to a useless energy for mechanical energy. So energy equation is still true. Energy equation is still true, but mechanical energy, because the friction, they will reduce. Thermal energy will increase. Okay?